Welcome to the Problems Channel Season 2, Episode 40, the episode which I titled When Triangles Kiss a Hyperbola, because in this episode we will solve a mathematical problem that deals with the areas of two triangles, each of which has precisely one vertex on a branch of the unit hyperbola. Before we do that, however, as a traditional and friendly reminder, if you have joined our channel mid-season, then first of all, welcome to our channel and thank you very much for your vote of confidence. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section find the episode titled The Problems Channel How To. Watch that episode in its entirety and follow all the instructions that were given that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E40, we're given the unit hyperbola whose equation is shown over here, but instead of working with the algebra of this single variable real-to-real function, we will be working with its geometric representation or with its partial graph. That is, we're told that a point P, for example, is chosen at random or arbitrarily on the negative branch of the partial graph of the unit hyperbola shown over here in red, and the point Q is chosen at random or arbitrarily on the positive branch of the partial graph of the unit hyperbola shown over here in red. Since we're dealing with a partial graph of a given function, it is evident that we also chose a certain orthogonal or Cartesian coordinate system with the y-axis and the x-axis, and to be pedantic, for this to be a legal and valid coordinate system, we also have to specify the origin. This is the point where the two axes intersect. Let's say we name this point O, but this is not that important. And we also need to specify the units of measurement along the x-axis and the y-axis. In this case, the scale is uniform. We measure the distances along the y-axis in the very same units with which we measure the distances along the x-axis. We're then told that the point P is projected orthogonally on the x-axis into the point P sub x, and the same point is projected orthogonally on the y-axis into the point P sub y shown over here. Likewise, the point Q is projected orthogonally onto the x-axis into the point Qx shown over here, and the same point Q is projected orthogonally onto the y-axis into the point Qy shown over here. And the author of this problem is somehow convinced that if we construct the following two triangles, the triangle QPY PX or QPX PY and the triangle P QX and QY, then the areas of these triangles will be one and the same, and the objective of the problem S2E40 is to show precisely that. The objective of this problem is to generate a convincing enough line of reasoning or a proof that the area of the triangle P, QX, QY, and Q, PX, PY is one and the same using the divide and conquer problem solving approach, which is the approach that we're studying right now in the dedicated fashion. As we mentioned in the previous episodes, if we want to apply the divide and conquer problem solving approach to the process of searching for a solution of this or that technical problem, that we should try to carry out the following three steps. First, we should try to divide a whole into a number of smaller and simpler primitive parts. Number two, we should try to find a solution for each and every smaller and simpler primitive part. And step number three, we should try to find a way to combine, to be pedantic, all the solutions of all the smaller and simpler primitive parts into a solution of the whole. However, in this description of the mechanics of how the divide and conquer problem solving approach works, in the step number 1, we left out the detail that in order to divide a whole into a number of smaller and simpler primitive parts, we need to have that whole in the first place. Sometimes in some problems, that proverbial whole is given to us explicitly. In other problems, even though that proverbial whole is not given to us explicitly, it is very straightforward to find it. We move literally one or two things. Oh, there it is. And we find our proverbial whole that can be fruitfully divided into a number of smaller and simpler primitive parts. Yet in other problems, we have to apply an effort of varying degree in order to recover that fruitful proverbial whole. And in this problem is exactly such a scenario where the whole that is a fruitful device that we can partition into a number of smaller and simpler primitive parts is not given to us explicitly. We are to recover it, and this is one of the amazing, interesting, and challenging things about mathematics, that many people look at one and the same object or objects in mathematics, but only some people see the winning candidate. So yes, this problem can be solved in a number of different ways. It is possible to construct the vector products. It is possible to use determinants, but in the fashion that we will be promoting throughout this channel at all times, keep it simple or make it as simple as possible, but not simpler, because even though right now we're dealing with the pronounced middle school mathematical objects such as triangles and graphs of the hyperbola, let's say, the glue that combines these elementary units of knowledge into a mathematical result, amazingly enough, will be actually one and the same when we step from the elementary mathematics into the world of grown-up mathematics. And again, when you mature enough and begin computing, let's say, automorphism groups in the theory of groups, or finding or discovering a uniform way to do it, then you will be evidently manipulating much more advanced and much more abstract concepts. But as my personal claim, based on my personal experience, the very glue which will put or unite these units of mathematical knowledge into a coherent whole will be exactly the same. As such, when we look at this particular diagram, what is the candidate for a fruitful whole in this case? In Season 1, Episode 1, we explained what mathematics is. In Season 1, Episode 2, we explained how to practice mathematics correctly. And we mentioned that nothing is actually to be gained if you just watch our solutions unfold all by itself without applying your personal effort. As such, if you could not solve this problem correctly on your own using the intended divide and conquer problem solving approach, then again, exercise this correct practice of doing mathematics. Listen for our hints, put this video on pause, walk away, think on your own, and the moment you realize what's going on, try to carry the solution forward all the way to the end on your own. As a first hint, there is a number of right triangles in the diagram shown over here. That's hint number 1. Think about it, put the video on pause, walk away, think on your own, see if you can unwind the solution from here. The hint number 2, among several right triangles that are hiding in plain sight over here, we suggest that you look, for example, at the right triangles PX, P, PY, and PX, O, PY, or likewise the right triangle QY, Q, QX, or QY, O, QX. And what does this information tell us? Well, the congruent right triangles, we have two pairs of congruent right triangles with a finite number of appropriate rotations, translations, and reflections, can always be put into what? Can always be put into a rectangle. So here, as a final hint, a fruitful whole that can be divided into a number of smaller and simpler primitive parts will be a certain rectangle. Now we suggest that you put this video on pause, walk away from this video, and think on your own. Yes, the blue rectangle that you saw just a second ago is my version of a winning hole in this case, but you can come up with a different idea. If you do, don't be shy. Please use the comment section to this video. Share your beautiful idea with us. And what is the motivation for the construction of this rectangle that we can refer to as the bounding rectangle? Well, let's, as I give you guys several hints in the previous segment, let's consider the right triangle PPX QX. What can you say about it? What is the congruent complement of this triangle? Well, the congruent complement of this triangle will be another right triangle that has what? The same, let's say, width of one side and the same height, let's say, that runs this way and this way. And if we consider the following right triangle, PX, QX, and Q, what will be the congruent complement of that right triangle? The congruent complement of this right triangle will be another triangle that has exactly the same, let's say, height and the same base and runs this way. And now, voila, we have our bounding rectangle, or our fruitful hole that can be partitioned into a number of smaller and simply primitive parts. And what is the motivation, or what is the driving idea behind this use of the congruent triangles? Well, the areas of these triangles is actually one and the same, as we mentioned a number of times. So again, of course, in real time, in the fog of war, or in the adrenaline rush to solve a problem, we do not really see the crisp solution or the crisp result which we chisel out during as we develop our solution. But certain hints and certain ideas float around in our mind, and the only thing we can do is say, let's try to investigate what will happen if. So now we can, once we take the journey all the way to the end, we solve the problem, we realize, yes, this is a beautiful hole that unlocks an elegant solution of this problem using the divide and conquer problem solving approach. We will throw all sorts of official language at it, and a way to construct the bounding rectangle in this case, or the winning hole, is as follows. Through the point P, let's say, we construct a straight line that is parallel to the axis Y, that goes this way, that runs this way, all the way. We do not need the remaining portion of this line here, but it runs this way. And likewise, through the point Q, we construct a straight line that runs parallel to the y-axis, like so, all the way through the point QX and all the way here. And by analogy, through the point P, we construct a straight line that is parallel to the x-axis and runs this way. And through the point Q, again, we construct a straight line that runs parallel to the y-axis, and that straight line will come from infinity there, pass through the point Q, pass through the point QY, run here, and these two pairs of mutually parallel straight lines will intersect at the points to which, let's say, we will refer. Let's say this point will be, this will be the point A, shown over here. The angle here is evidently right. That is straightforward to prove. And here, when this straight line through Q and this straight line through P intersect over here, let's refer to this point as the point B, and voila, we have our bounding rectangle that can be fruitfully partitioned into a number of smaller and simpler primitive parts, and we will consider that partitioning in the next segment. And now that we have our bounding rectangle, that is the proverbial hole, we execute the first step of the divide and conquer problem solving approach pretty much automatically. And that step suggests that we divide the whole into a number of smaller and simpler primitive parts, and in this case, the division of the whole or division of the bounding rectangle A, Q, B, and P unfolds pretty much all by itself, which is, by the way, also sometimes a result of a fruitful and beautiful mathematical idea. You see, there is no symbolic shuffling, there's generation and regeneration, combination and recombination of mathematical ideas, because a mathematical idea is the first-class citizen in mathematics. And due to this beautiful idea, the first step of the divide and conquer problem-solving approach unfolds all by itself. That is, we can represent our bounding rectangle A, Q, B, and P as what? As the union of the following triangles. I wrote this union representation of this bounding rectangle over here on the top line. On the bottom and the left segment, I will show the second partition, but fundamentally our proverbial whole, the rectangle AQBP, can be partitioned or tiled tight with no gaps and no overlaps into a union of the following triangles. The triangle QPXPY, this is our usual suspect, QPXPY. QPXPY, this is this guy right here. We need to say something about the area of that triangle. And the following three complementary right triangles. PXAQ, that is PXAQ, this right triangle. This is nothing but props that I cut out from the cardboard, guys. You can see it right here. And in the next segment, you will see this guy right here. No magic over here. Some scissors, a ruler, and some glue. And this triangle over here, we understand what it is. PXAQ, PXAQ. Next is QBPY, QBPY. It's this guy right here. This gentleman right here, QBPY. And the last right triangle is a show of P's. PY, PPX. This is this guy, PY, PPX. Again, this usual suspect over here. And the reason I refer to these right triangles as complementary, because they complement the area of our usual suspect number one, the triangle QPXPY, and make up the area of the bounding rectangle. This is one way to partition our whole. And what is the second way to partition our whole? The second way to partition our whole will be shown in the next segment. And the second way in which one and the same whole, the bounding rectangle AQBP, can be partitioned into a collection of smaller and simpler primitive parts, or the way in which the whole can be tiled tight with no gaps and no overlaps with the corresponding triangles, is the following. The rectangle AQBP can be represented as the union of the triangle PQXQY. This is our usual suspect number two, this triangle right here, shown over here, and this is the triangle PQXQY. We can see it in the open, and the other guys, our props, surround this or complement the area of this triangle to the area of the bounding rectangle. Unionized with the triangle PAQY, PAQY, this triangle right here, unionized with the triangle QYQQX. This is the show of Q's, just like the show of P's over here on the top. The triangle QYQQX, QYQQX, this triangle right here. This prop unionized with the triangle QXBP, which is what? QXBP, this triangle right here. And now, since we tiled one and the same whole, one and the same bounding rectangle AQBP in two distinct ways, what is our battle plan? Well, technically, we carried out the first step of the divide and conquer problem solving approach. That is, we identify the fruitful whole, and we partitioned or we divided that whole into a number of smaller and simpler primitive parts. One of these smaller and simpler primitive parts are our usual suspects, the rectangles Q, Px, Py, and Pqx, Qy. We will not be computing their area directly, but we will show indirectly that the areas of these two triangles is actually one and the same. How? Well, if we apply the area operator through our unionization, in some sense, we will have what? The area of the bounding rectangle AQBP will be represented what? As the sum of the areas of this triangle, the area of this triangle, the area of this triangle, the area of this triangle. And in the same way, the same area of the bounding rectangle AQBP can be represented as the sum of the areas of this triangle and this triangle and this triangle and this triangle. Nothing more than the literally middle school arithmetic. Now what we will say? Well, we will express the area of this triangle as the difference between the area of this triangle and the areas of the remaining three triangles. And we'll represent the area of this triangle, PQX, QY, as the difference between what? Between the area of the bounding rectangle, AQBP, and the areas of these three triangles over here. But because the area of the bounding rectangle AQBP is what? Is one and the same. We will not even bother computing that area. It is one and the same. And we subtract two different quantities from one and the same quantity. So if we show that these two different quantities actually amount to one and the same real number, voila, we have proven that the area of the triangle QPXPY is equal to the area of the triangle PQXQY as requested, and we will carry out these straightforward computations in the upcoming segments. Now that we carried out the first step of the divide and conquer problem solving approach and we identified a fruitful whole, which is the bounding rectangle AQBP, and we produced two distinct but equivalent in some sense partitions of that one and the same whole, one and the same rectangle in two different ways, we're stepping into the weeds of the second step of the divide and conquer problem solving approach, where we are prescribed to solve each and every smaller and simpler primitive part. What does it mean to solve each and every smaller and simpler primitive part in this case? In this case, to solve each and every smaller and simpler primitive parts means to express the area of each underlying complementary right triangle, express the area of these triangles through the locally available material. That is, in the first case, let us concentrate on the triangles Q, B, Py, and Qx, B, and P. It will be this. We'll concentrate on this complementary right triangle here, and another one that was, let me see where it was, and this guy right here. See, these two right triangles. We want to solve these smaller and simpler primitive parts, means to express the areas of these right triangles through the locally available material. What is the locally available material? The locally available material in this case, instead of using the notation Qx, Py, Px, and Qy, that is a little bit awkward. We will invert that notation and we will represent the coordinates of the point P as xp and yp, P was as a subscript, and we'll express the coordinates of the point Q as xq and yq, correspondingly here and here and here and here. As such, I will go slowly and thoroughly for the area of the, let's say, right triangle. Which one is it? This triangle, let's say QBPY. Slow and thoroughly. QBPY. Triangle Q, B, and PY. What is it? Well, this is the half product of the length of the base, half product of the length of the base, let's say BPY, times the height QB, the length of the line segment QB, and through the locally available material. What does that mean? Well, that means 1/2 over what? What is the length of the base in this case? Well, the length of this base is, through the locally available material, is the coordinate of the point QX, or XQ, times XQ. We take it with a positive sign. We take it as it is because this number is positive and this number is positive. And what is the height of this triangle, the line segment QB? Well, this can be represented as a composite quantity, the length of the line segment QX plus the line of the line segment, let's write it down, QX plus QXB. You see, this is what it is. But now we express the length of this line segment through the locally available material. I'll erase these symbols in a minute. You guys keep good records on paper in your area. So what is the magnitude of the length QX? Well, that magnitude is actually the coordinate 1 over XQ. You see, because this point belongs to the unit hyperbola, I move this equation over here. Y equals 1 over x. If x is x sub q, then what is y? This distance right here, this distance is y, 1 over xq. What about the QB, the length of the line segment QB? Well, the length of this line segment is again given quite nicely. All we have to do is keep things in the positive. Technically, this is 1 over xp, but because this number, again, technically is negative the way this branch sits, we carefully write down 1 over absolute value of xp, and this is it. Now we open up the parentheses, and what do we have? xq and xq cancel each other out, and what do we have? We have exactly 1/2 plus xq, let's write it down, xq over 2 absolute value of xp. And this is the area, you see, this is the area of the triangle QBPY. This is the expression that captures the area of the triangle QBPY. Now let's write down the expression for the area of the triangle, smaller and simple primitive part, QX, B, and P. Or, in other words, this triangle right here. To keep it more visual for you, to make it easier for you to see what we're doing, we want to express the area of these smaller and simpler primitive parts in terms of the locally available material, which is what? The length of the line segment PB, which is, again, in this case, it is a composite quantity. If we want to keep things positive, what do we have to write? It's 1/2 over the sum of what? Absolute value of xp, absolute value of xp, plus this length, the length of the line segment PYB, is the same as the length of the line segment OQX, which is what? Which is xq. That is the number xq, times the height of this triangle, times, again, one more time, times the height of this triangle. And what is the height? It's 1 over the absolute value of the point xp. 1 over absolute value of xp. Now, let's carefully examine what do we have over here. Once we open up the parentheses, xp and xp cancel each other out. xp here in the numerator, xp in the denominator cancel each other out, and we still have 1/2, still 1/2. And what do we have here? xq over 2 times xp. xq over 2 times xp. And voila, we just proved that the areas of these two smaller and simpler primitive parts, let's keep it this way, and this guy right here, see if we can unwind them in a reasonable way. Voila, there you go. Let's replace it, the string of symbols with its official, it's equal to the area of the triangle, which one? qx, 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 bp. The area of the triangle qbpy is equal to the area of the triangle qxpb, qx, I'm sorry, bp, bp. And at this point, what can we do? We can cross out these two triangles, triangle qbpy. Where is this guy? qbpy, this guy, qbpy, and qxbp, qxbp, this guy. We can cross these two triangles out from our unionization and the corresponding areas. And we can move on to the remaining two pairs of triangles, and we will carry out the relevant computations in the next segment. Now that we solved two smaller and simpler primitive parts, the triangles QBPY and QXBP, meaning we express the areas of these two planar triangles in terms of the locally available material, we'll move on to the solution of the next pair of smaller and simpler primitive parts, the triangle PYPPX and the triangle QYQQX, using our favorite props, this triangle over here, QYQQX, this guy, and the right triangle PXPPY, this triangle right here. These are complementary right triangles, and the areas of these triangles will unfold as follows in terms of the locally available material. Let us write down the expression for the area of the triangle QXQQY, QXQQY. What is the area of this right triangle? Well, again, it's a half product of, let's say, the length of the base, QYQ, and the length of the height, QQX. The length of the base, QYQ, the length of the line segment, QYQ, is the same as the length of the line segment, OQX, O, which is the x-coordinate of the orthogonal projection of the point Q on the x-axis. So this will be 1/2 times xq times, what is the height of this triangle, or what is the length of the line segment QX? Well, if xq is the coordinate of this point and the point Q belongs to the unit hyperbola, then y is 1 over xq, 1 over xq. These two numbers cancel out and we get the area of 1/2. Wonderful. What can we say about the area of the complementary right triangle PXPPY? Well, exactly the same thing. The area of the complementary right triangle PXPPY is half product of the length of its base, PPX, and its height, PPX. And what is the length of the line segment PYP? It is the same as the length of the line segment OPX. And in terms of the locally available material, what is this point? This point corresponds to the XP. So the area of the triangle PXPPY is 1/2. 1/2 times what? The absolute value of the coordinate xp times. What is the height of this triangle? If xp is the horizontal coordinate, then the vertical coordinate of the point P that sits on the negative branch of the partial graph of the unit hyperbola is technically 1 over xp, but because this number is negative, we take its absolute value. So the height will be 1 over absolute value of xp. Again, the absolute values cancel each other out. We get 1/2. This is one and the same number. So these two areas are actually one and the same, and we can take care of these triangles. We can cross them out. We show that the areas of these triangles, this triangle and this triangle is one and the same. And what is left to do? We need to analyze the area of the triangle PXAQ and the area of the triangle PAQY, and we will do that in the next segment. So far we have solved 4 out of interesting 6 smaller and simpler primitive parts. That is, so far we were able to express the areas of the triangles PY, PPX and QY, QX, and the triangles QB, PY and QX, BP through the locally available material. And now we just have to do the same exact thing for the remaining 2 interesting smaller and simpler primitive parts, or the complementary right triangles shown over here, PAQY, it is this triangle, this usual suspect here, and the triangle PX, A, and Q, this triangle shown over here. I already prepared the expression for the triangle, for the area of the triangle PAQY. And what is the area of the triangle? The area of the triangle is a half product of the length of its base and the length of its height. The length of its base in this case is the length of the line segment QYA, which is what? Again, is the length of the line segment OPX. And what is the distance from the point O, the origin of our orthogonal coordinate system, to the point PX, which is the orthogonal projection of the point P on the x-axis? Precisely, this is our value xp, but because all these magnitudes have to be taken with a plus sign, we're working with the positive quantities. We need to take the absolute value of that magnitude. It will be 1/2 times absolute value of xp times what? In this case, the height of this triangle, or the length of the line segment AP, can be represented as what? As a composite quantity, which is the sum of the line segments A, PX, and PXP. And in some sense, again, I'm not spending too much time on it because I think that you guys should be able to do it on your own. But here, recursively, we have yet another divide and conquer, whole, parts, solve, combine, and so on. You should actually say these words. But here, the length of the line segment APX is the same as the length of the line segment OQY, because we have a rectangle over here, the small rectangle. And what is the length of the line segment OQY? Well, this is the y coordinate of the point Q, and if the point Q sits on the positive branch of the partial graph of the unit hyperbola, whose equation is shown over here, y is equal to 1/x, and xq is the x coordinate of the point. What is the y coordinate of the point? 1/xq. 1/xq plus the length of the line segment PYP. And what is the length of that line segment? The length of that line segment corresponds to the positive version. We agree to work with positive quantities, positive version of the y coordinate of the point PY, or the orthogonal projection of the point P on the y-axis, this distance right here. In other words, the length of the line segment PXP is equal to the length of the line segment OPY, which is, again, in its positive incarnation, would be what? Because the point P sits on the negative branch of the partial graph of the unit hyperbola, 1 over absolute value of xp. And now we carefully open up the parentheses, and what do we have? Absolute value of xp in the numerator times the absolute value of xp in the denominator cancel each other out. We have, again, our favorite 1/2 plus what? The absolute value of xp over 2 times the value of xq for this product right here. And we bravely put the equal sign because we see already understand where it's going on. And by the way, to make your work with the material that we'll present on this channel more fun, you can zoom in and out or put our video on pause the moment you understand what's going on. work on your own, come back in, compare your ideas to ours, go like that back and forth until you complete the solution. So here, once we're done with the area of the triangle PAQY, we take it off. And what's left is to analyze the area of the triangle, complementary right triangle, PXAQ. How can we represent the area of the triangle? Again, half product of its height, the length of the line segment APX, and the length of its base, the line segment Q and A. In this case, unlike in the previous case where the height was a composite quantity, here is the base is a composite quantity. Again, a recursive incarnation of the divide and conquer. I will not talk much about it, but here is 1/2 times what? The length of the line segment AQ, which is a composite quantity, that can be represented as the sum of the line segments QY and QYA. And what is the length of the line segment QYQ? It is the same as the length of the line segment OQX. And that is what? This is the point XQ plus the length of the line segment QYA, which is the same as the length of the line segment OPX. And what is the point PX? Is the orthogonal projection of the point P on the x-axis. In order to work with the positive quantity, we take absolute value of that point P. And what do we multiply this by? We multiply this by the height of our triangle, or the length of the line segment PXA, which is what? Exactly this line, the length of the line segment PXA is equal to the length of the line segment OQY. And what is this line segment represent? This line segment represents the y coordinate of the point X that sits on the positive branch of the partial graph of the unit hyperbola. And what is that? This is 1 over XQ. 1 over XQ. And now if we open up the parentheses, what will we have? XQ in the numerator, XQ in the denominator cancel each other out. And what do we have left? 1/2. This is 1/2 shown over here. And 1/2 times the absolute value of XP times 1 over XQ. This is precisely this term, the absolute value of the coordinate XP over 2 times XQ. Again, the same exactly expression that represents this time what? This time represents the area. Let's write it down. The area of which triangle? PXAQ. PXAQ. And what can we do now? We can cancel out this two triangles again. PXAQ is this guy. We'll cross it out this way. And the area of the triangle PAQY, this guy. And now we're done with the second step of the divide and conquer problem solving approach. In other words, we managed to solve each and every smaller and simpler primitive part. And now we will carry out the third and the final step of the divide and conquer problem solving approach. We will find a way to combine all the solutions of all the smaller and simpler primitive parts into a solution of the whole. The third and the final step of the divide and conquer problem solving approach prescribes that we find a way to combine all the solutions of all the smaller and simpler primitive parts into a solution of the whole. Now we carried out the second step. We managed to find all the solutions of all the primitive parts, which in this case amounted to what? In this case, the solution of each and every smaller and simpler primitive part amounted to writing down the expression for the area of the respective complementary right triangle in terms of the locally available material. Here we capitalize heavily on the fact that the points Q and P sit on different. Initially, in the next segment, we'll take a look at the case where both points sit on the same branch, but here the points Q and P sit on the different branches of the partial graph of the unit hyperbola. And we capitalized on the fact that the y coordinates of these points, of their projections on the corresponding y-axis, can be expressed precisely which way? Well, 1 over xp in the first case because of the relationship between the real numbers y and x, and in this case it will be 1 over x q for the point q, and when folded, all the expressions for the areas of the complementary right triangles. And one by one we paired up these triangles in the following way. We showed that the area of the triangle PYPPX and QYQQX is one and the same. I showed these two triangles with the double. We crossed it with two red lines. We showed that the area of the triangle QXBP and the area of the triangle QBPY is one and the same. I crossed it with one red line that runs this way. And in the third segment, we showed that the area of the triangle PXAQ is the same as the area of the triangle PAQY. And in the sense, that is precisely what it means to find a way to combine the solutions of all the solutions of all the smaller and simpler primitive parts into a solution of the whole. That find a way to combine eventually, or actually, came out to showing that the expressions for the areas of these triangles, let's pair them up, for example, with yellow. Let's see if you guys can see the curly yellow. So these two triangles will be paired up this way. Here, this triangle will paired up with this triangle, and these two guys will be paired up this way. We showed that pairwise the areas of these triangles, shown in the lower right corner of your screen, are equal one another. And that means what? The areas for these two triangles will be what? The difference between the one and the same quantity, the area of the bounding triangle AQBP, and the total, the aggregate areas of these triangles, but the areas of these triangles pairwise are the same. Consequently, this proves with nothing but the proverbial and actual middle school arithmetic that the area of the triangle QPXPY is the same as the area of the triangle PQXQY. Where is it? P, QX, and QY. These two triangles have one and the same area. And now this is actually another level of, let's say, higher abstract cognition. Every time you solve a problem, you want to see if it's a good idea, or you want to see if you can throw a little bit of physics into the underlying mathematics. This is always a fun and good idea because mathematics and physics enjoy mutually beneficial relationship, and conversely, as a matter of fact, we will talk about it in the upcoming episodes. One stage of solving a problem in physics actually amounts to reducing the physics of the underlying phenomena to mathematics, at which point mathematics takes over. So whenever you solve a problem in mathematics, see if you can throw some physics into it, and conversely, when you will be working with a problem in physics, the mathematics will be unleashed upon you automatically by default, because physics without mathematics is not physics. It's some sort of shystery and absolute nonsense that is not acceptable. But here, let's say we now make the point Q move. So now from the static situation, we step up into the exciting world of motion. Now things begin to move. Let's say the point Q orbits the trajectory of the positive branch of the partial graph of our unit hyperbola, and the point P orbits in some way the negative branch of the partial graph of the unit hyperbola. So in our minds, or maybe with your favorite software such as GeoGebra, for example, we can put an animation together and show that when the points P and Q move on the respective branches, the areas of the triangles that are formed as explained will actually stay what? Will remain one and the same. This is actually quite cool and quite exciting. And for a bit of physics trivia, what does this situation remind you of? Put this video on pause, walk away from your computer, think about it, come back and compare your idea to ours. My idea is that this situation with the points P and Q moving over the respective branches of the partial graph of the unit hyperbola reminds us of what? Reminds us of the Kepler's second law of motion, which says that when a planet, I will exaggerate things greatly. Let's pretend that this is an ellipse, and one of the foci of the ellipse over here, this is the sun, this is the planet P. The radius vector, according to the second law of Kepler, the radius vector of the planet P that transcribes, let's say in its most general case, an elliptic orbit with the sun in one of its foci, will sweep the same areas in the same amount of time. So if this is delta t, then the area of this elliptic segment will be the same as the area, let's say, swept over here, if this is the same delta t. If the planet travels from this point to this point during the same time as it does over here. So these two areas will be the same, and the intuitive explanation apparently is that when the planet is further away from the sun than it is closer, it slows down a little, and when it gets closer to the sun, it accelerates, it speeds up a little, so it covers the distances here from the foci to the planet, from the sun to the planet, is a little bit less compared to this distance, but here the planet travels a little bit faster than it travels when it's further away from the sun. And this is one analogy that we can come up with between mathematics and physics. Now, as the problem was given to me and the way I solved it, as I showed over here, the points P and Q were explicitly stated to be on the distinct branches of the unit hyperbola, but it is perfectly normal to investigate the case when the points P and Q are located on the same branch of the unit hyperbola. Negative or positive doesn't matter. For demonstration purposes, I will consider in the next segment the case where both points are located on the positive branch of the unit hyperbola. If you're not interested, that segment is optional. You can skip forward to the next challenge. In this segment, which is optional, if you're not interested what we have to say about this problem in this segment, feel free to fast forward to the next challenge. But here, for the curious souls, we consider the case when the points P and Q are chosen on one and the same branch of the partial graph of the unit hyperbola. Now, these points evidently can sit both on the positive branch or both on the negative branch of the graph of the unit hyperbola, and in each of these scenarios, the points P and Q can be located with respect to each other in different configurations. For example, the point P can be located above the point Q with respect to the x-axis or below. Again, all these configurations will lead to one and the same result, but this is perhaps one of the less glamorous parts of geometry, is that where we have to consider these cases separately and technically on the books for publication and so on, we have to consider all the cases. Points P and Q on the positive branch, points P and Q are both on the negative branch, the point P above the point Q in each case, and the point P is below the point Q in each case. Here, for demonstration purposes, we only consider one case. As a lightweight homework assignment, you can analyze the other cases on your own. And again, in order to derive the maximal academic benefit from working with the material that we present on this channel, we suggest that you do not just mechanically watch what I have to say about this problem, put this video on pause, walk away the moment you understand what's going on, run with this idea with your understanding on your own, try to unwind the solution of the problem on your own, come back and compare your solution with ours. If you get stuck, you can use my ideas to get unstuck, or maybe it's also possible that you will have a much better idea, much brighter idea. By all means, share it with our community in the comment section. So here, let us say that the points P and Q are located on one and the same positive branch of the graph of the unit hyperbola. And it so happened that the point P with respect to the point Q is located above when it comes to the y coordinates of these points as shown over here. Again, we already know the motivation. Any two congruent right triangles with a finite number of rotations, translations, and reflections can be put together into a rectangle. So here, what is the bounding rectangle? The bounding rectangle in this case is the origin of our orthogonal coordinate system O, then the point Py in this configuration, A, and the point Qx, where how do we obtain the point A? Well, in some sense, in the previous case, when the points P and Q were located on the distinct branches, we had to construct two pairs of parallel lines to the y-axis and one pair parallel to the x-axis here. These straight lines from the previous case already are drawn for us by the x-axis and the y-axis, and the only thing we have to do is to construct what? A straight line through Q parallel to the y-axis or perpendicular to the x-axis, and a straight line through the point P that is parallel to the x-axis or perpendicular to the y-axis. These two straight lines will intersect at the point A, and this is the point that completes our bounding rectangle. O, Py, A, Qx. This is our proverbial hole. We partition it. You already know the drill, the union, the tight tiling with no gaps and no overlaps. We apply the area operator. We convert the union into the sum of the areas and so on. And now we consider what? Let us consider the area of the triangle PYAQ, this triangle, PYAQ, and the corresponding triangle then PA and QX. For the area of the triangle PYA and Q, what do we have? Well, it will be half product of the length of the base of that triangle, which is what? The length of the line segment PYA is the same as the length of the line segment OQX, and the point QX is displaced from the origin of our orthogonal coordinate system by how much? By the xq. So this will be 1/2 times xq times what? This time the height of our complementary right triangle, or the length of the line segment AQ, will also be a composite quantity, but in this case it is perhaps more correct way to say it is a part of a composite quantity, and instead of the sum, remember in the previous cases we had 1/2 plus something, here this 1/2 will come out with a negative sign. Why is that? Well, the length of the line segment AQ is the length of the line segment AQX minus the length of the line segment QX. Let's write it down. It will be the length of the line segment AQX minus the length of the line segment QX. You see, this is how this cookie crumbles this way. You see the length of the line segment AQ. This is the length of the line segment AQ, and now that we understand what's going on, this is 1/2 times xq times what? What is the length of the line segment AQX? This is the y coordinate of the point P, so it's 1 over xp, this time with the plus sign because we work in the first quadrant. All the magnitudes are, all the real numbers involved are positive, minus the length of the line segment QX, which is what? Which is the y coordinate of the point Q, minus 1 over xq. And what do we have? xq in the numerator, xq in the denominator, 1/2. There you go. xq over 2xp minus 1/2. This is the area of the triangle PYAQ. PYAQ. Now for the area of the triangle PAQ. qx. p a qx. I will write it down. I will work a little faster. We'll all understand what is going on. Half product of the height of the triangle PAQX. So this will be 1/2 times, what is the height over here of this triangle? It's 1 over xp. 1 over xp. That's the height of the triangle. That's the vertical displacement of the point P from the x-axis, times the length of the base. But this time, the length of this base is what? It participates as a composite quantity in the line segment APY. So what is it? Times the length of the line segment APY, which is xq, minus the length of the line segment PYP, which is what? XP. That's right, minus XP. And what do we have? So what do we have here? XP in the denominator, XP in the numerator comes out to what? Minus 1/2. Minus 1/2. And what do we have here in the numerator? XQ over 2 times XP. And voila, what do we have? One expression, another expression. They're actually one and the same. So the area of these two triangles is one and the same. And likewise, we keep working with the remaining two complementary right triangles. In this segment, we will analyze the relationship between the areas of the following triangles. The triangle QY, PY, and P, the right complementary triangle QY, PY, and P, this guy, and the area of the triangle PX, QX, and Q, this time smaller complementary right triangle. What do we have for the area of the triangle QY, PY, P? Half product of the base. What is the base? Is the horizontal displacement of the point P from the y-axis or from the origin here. So it will be 1/2 times xp times what? The height of this triangle, or the length of the line segment PY, QY, is what? The difference between the height of the point PY above the x-axis. So this will be what? 1 over xp minus the length of the line segment OQY, which is the vertical displacement of the point QY above the origin y. So this will be 1 over xq. 1 over xq. And in this case, what expression do we get? Xp in the numerator, xp in the denominator. Again, it will be 1/2 minus what? Xp over 2xq. Very nice. What do we have for the area of the complementary right triangle PX, QX, and Q? Again, this will be half product of, this time the height of this triangle is quite evident. It's the vertical displacement of the point P from the x-axis. So this will be 1 over xq times the length of the base. This time the base participates in a composite quantity. The difference between the length of the line segment OQX, which is what? Which is the xq point coordinate, and the difference and the length of the line segment OPX, which is what? XP. And what do we have here? In this case, let's complete this expression over here. XQ in the denominator this time, XQ in the numerator cancel each other out. We have 1/2 minus what? XP xp in the numerator divided by 2 times x cubed. And when we compare the two expressions, what do we have? One expression for the area of the triangle pxqx and another expression for the area of the triangle qy But these expressions are evidently equal one another. They are the same, so the areas of these two triangles also equal one another. And in the next segment, we will just have to compare the areas of the remaining two complementary right triangles. Wonderful, and now we only have to analyze the relationship between the areas of the following triangles, complementary right triangles, PYOPX. This is PYOPX. I'll hatch this triangle in blue, so hopefully you can see it better. It runs all the way down here. It sits on the partially on the x-axis, and the area of the complementary right triangle QYOQX or QYOQX. I'll cross hatch it which way? This way. So in yellow, we want to compute the area of this here complementary right triangles. We already understand where this is going, but we want to be good citizens of mathematics and carry out this proof completely. So what do we have for the area of the complementary right triangle PYOPX? Evidently, it's a half product of what? The base, which is the length of the line segment OPX, which is 1/2 times XP times what? Times the length of the height of this triangle PY, or the length of the line segment PYO, which is what? Is a vertical displacement of the point P with respect to the x-axis, or the y coordinate of the point P, which sits on the positive branch. Consequently, we already know the drill. The height of this triangle will be 1/xp. Now, xp in the numerator, xp in the denominator cancel out, and we get the beautiful answer of 1/2. What do we have for the area of the complementary right triangle QYOQX? Again, 1/2 of the product of a length of its base, which is what? Which is the distance from the origin of our coordinate system, the point O, to the point QX, which is the orthogonal projection of the point Q onto the x-axis, which is our favorite number xq. The coordinate xq, this is a strictly positive real number, times the length of the height. What is the height of this triangle? The height of this triangle is the length of the line segment QX. And what does this height represent? This height represents the vertical displacement of the point Q over the x-axis, and because this point Q sits on the positive branch of the graph of the unit hyperbola, we know the drill. That coordinate will be 1/xq, 1/xq, and what do we have in the result? In the result, we have xq in the numerator, xq in the denominator. These two guys cancel each other out. We have 1/2. This is one and the same real number. These areas equal one another, and since we covered all the possible complementary right triangles, which tile our, again, proverbial hole or the rectangle OPYAQX tight with no gaps and no overlaps, then the areas of the triangles at hand, the triangle, which one is it? Q, PX, PY, and the triangles, and the triangle, which one, where is it? P, QY, QX, shown in yellow over here. These two triangles have the same area nonetheless, as shown over here, even when the points P and Q are located on the same branch of the graph of the unit hyperbola. And again, this is one way in which mathematics is understood and developed. And in my humble, unprofessional opinion, that can be done only in one way, through an organic or a synthetic understanding of what is going on. You can throw as many symbols at a problem as you want. If you do not possess, if you do not have a good and solid organic or synthetic understanding of the local material, no amount of vector products or determinants will actually help you understand the nature of the phenomenon at hand and obtain maybe a new and interesting result. This is exactly how these results are obtained. Organic understanding of the local material, you step up close and personal with the local material, you cross the blades with the pirate, so to speak, and as you develop a better and better organic understanding, or you develop a better and better organic understanding of the material, you can come up with better and deeper ideas. You can start abstracting it and developing it more and more and more, and eventually 10 years later, after a concentrated effort, you come up with some deep and interesting results, and only 5 people on the face of this planet can understand what are you talking about. In any case, this is it for the mathematical problem S2M42, and we will move on to a new challenge next. As we have seen in this episode, it pays to develop the ability to see as simple as possible, but not simpler in mathematics and in theoretical physics and in computer science. And this is exactly what you are invited to practice, to try to do in our next challenge, which will be the mathematical problem S2M43. In this problem, we're given a set of whole positive numbers AI such that all these numbers are odd or not divisible by 2. All such numbers are coprime with 5 or do not have 5 in its prime factorization. And these numbers, which are odd and 5 coprime, they vary between 1 and 100. Under these conditions applied to the whole positive numbers AI, we are asked to compute the value of the following finite product. This product is constructed on the values of the trigonometric function of cosine, whose argument looks like the numbers AI mentioned over there, scaled by pi and divided by 100. This is the argument to the trigonometric function of cosine, where AI varies between 1 and 100, and each such number is odd, and 5 coprime, meaning that each such number is coprime with 5. We suggest that you try to use what you have learned so far about the mechanics of the divide and conquer problem solving approach and apply that approach to the process of solving this problem or recovering the real number, evidently, that sits on the right hand side of this finite product. Why? Because the cosine of a real number here is again a real number, and the set of all real numbers with 0 thrown out forms an infinite and commutative group under the operation of multiplication, with the identity of the group being the number 1, which means that the product of any two real numbers is again a real number where the numbers are not 0. Every such number has the multiplicative inverse and so on, which means that a finite product of real numbers is a real number, and we're looking to unmask or to reveal the name of that real number that sits behind this finite product. Good luck to you guys with this challenge, and thank you for your time. Thank you for watching this episode, and I will see you in the next episode, in which I will share my solution of the mathematical problem S2M43.